Hi, everybody. So, in today's video, we're going to be really pulling together a lot of the ideas from this module and looking at some sample AP FRQ questions that relate to this chapter. So, we're really looking at one particular type of FRQ question that links together a lot of these ideas. My plan right now is to do two practice questions with you to show you how these ideas are linked together, as well as how they connect to other ideas that we've talked about throughout the year. And then our plan is to have you guys practice with these ideas and these FRQ questions when I see you again in class. So let's start with one of the FRQ questions from 2016. This was actually question 4 on that AP test. Consider the differential equation. So the students on this test were given this differential equation, dy over dx equals y squared over the quantity x minus 1. The first thing they were asked to do is, for part A, on the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. Now, while it is possible to do this in your head or just by kind of thinking about it, I find I am less likely to make a mistake when I have an organized list of the points and the slopes that I calculate. So I would start by having x, y, and then the calculated dy over dx, or slope, that I get by using those values in my differential equation. Now, the 6 places on the graph where we're asked to draw the slope are 0, 2, 0, 1, 0, 0, and 2, 2, 2, 1, and 2, 0. If I take this x and this y and I substitute them, the y is 2, so I would have 4 divided by -1, which is -4. If I substitute 0 and 1, I would have 1 divided by -1, which is -1. If I substitute 0 and 0, I would get 0. If I substitute 2 and 2, I would have 4 divided by 1, which is 4. If I substitute 2 and 1, I would have 1 divided by 1, which is 1. And if I substitute 2 and 0, I would have 0 divided by 1, which is still 0. Now what I'm going to do to visualize the solution to this differential equation by graphing a slope field is I'm going to graph little tiny pieces of lines with these slopes. So at the point 0, 2, I would graph a slope of -4, which is going to be steeply negative. At the point 0, 1, I'm going to graph a slope of -1, which is a little less steeply negative. 0, 0 is going to have a slope of 0. And remember, that means it's a horizontal line. The slope is 0. At 2, 2, my slope is 4. At 2, 1, my slope is 1. And at 2, 0, my slope is 0 again. And that is my differential equation. Now, when AP graders are grading this question, they are asked to look for two different things. Is the direction of your slope correct? So are the positives going in the positive direction and the negatives going in the negative direction? And are the zero slopes correct? So did you graph that the slope of 0 was a horizontal line? A couple pieces of advice that I have for you. Do not graph extra slopes. If that point on the graph doesn't have a dot on it, don't graph the slope there, because anything that you do that's extra, if you happen to make a mistake, will count against you. So you want to make sure you only do what you're asked to do and nothing more than that. For part B, it says let f of x be the particular solution to the given differential equation with the initial condition f of 2 equals 3. Now it says here, write an equation for the line tangent to the graph at x equals 2. So the directions here are to write the equation of a tangent line. Then use your equation to approximate f of 2.1. So after that, the second part of this question is to get an approximation. I'm going to do this in 2 steps, and I'm going to make sure that after I find each piece of this answer, because there are 2 parts to this answer, the tangent line and the approximation, I'm going to make sure to highlight that I really did that. So on the AP test, I would put a box around that to show that I did both parts. Step 1 is to write the equation for a tangent line. Anytime you are asked to write the equation of any kind of line in any kind of math class, you always need 2 pieces of information. You need a point and you need a slope. Now it tells me here in the instructions that the point is f of 2 equals 3. So the point would be 2, 3. The slope of a tangent line is the derivative. So, since we were given the derivative in the original instructions way back at the top, I'm going to use this equation to find the slope of the line that I'm writing the equation for in part B. So I would have dy over dx evaluated at 2, 3. Now you want to make sure to show your work carefully here. Show that you're taking the derivative function and plugging in your value. Because sometimes, not all the time, but sometimes showing that work, that you understand the calculus process, can actually get you partial credit for a question where you end up with the wrong final answer. So what I'm going to do now is I'm going to plug in the y, which is 3, and the x, which is 2, and I get 9 divided by 1, which is 9. That means that my tangent line, and you'll notice that I'm labeling that this is the tangent line, would be y minus 3 equals 9 parentheses x minus 2. Part of the reason I label this is when the AP graders are grading this, one of the things they look for is, did you know that to find the slope you needed to use the derivative? So by showing my work, by saying the slope was the derivative with this number plugged in and here's what I got, a lot of times I can get myself some partial credit for demonstrating an understanding of knowledge there. The other reason I'm labeling this is that the first part of the question asked me to write the equation of the tangent line. So by saying tangent and writing the equation of a line, and then putting a box around it, I make it very clear to the AP grader this was the answer that I got for the first part of the question. Now, the second part of the question is to use the equation to find f of 2.1. In order to do that, I want to rewrite this equation where the y is by itself, because that's going to enable me to plug in my number. When we did this earlier this year, we called this a linear approximation or a linearization. So all I'm going to do is I'm going to rearrange this equation by adding this 3 to the other side, which means I have 9 parentheses x minus 2 plus 3. In order to find f of 2.1, I'm going to replace the y with f of 2.1. And again, I'm doing this and I'm being careful about my notation because it shows the AP grader that I understand that to find the approximation to the original function, I'm using the tangent line. Equals 9 parentheses 2.1 minus 2. I'm just substituting the 2.1 for the x plus 3. Now 2.1 minus 2 is just 0.1, and 9 times 0.1 is 0.9. So my final answer here would be that f of 2.1 would be approximately 3.9, and I would put a box around that answer. The reason, again, that I'm putting a box around that answer is to show that I've done both parts of the question. Here's part 1, write the equation of the tangent line. Here's part 2, use that equation to make an estimate. Now, part C to this question is my favorite part because this is the part that we've been practicing, and it's really fun for me to do this. It says, find the particular solution to the given differential equation with the initial value f of 2 equals 3. Those directions should look pretty familiar. We've been practicing it a lot. Finding a particular solution to a differential equation means find the original function. So we're going to go back to our separation of variables process. Now I know that I need to separate the variables here because the equation has x's and y's. And separating my variables is always my first step when there's x's and y's in the same problem. To do this, I'm going to, and this is going to be a little bit hard to think about, divide by y squared. And I'm dividing because y squared is on the top, so to get rid of it, I need to divide. And multiply by dx at the same time. So I would have 1 over y squared times dy equals 1 over x minus 1 times dx. Now I'm going to integrate on both sides, which means I like to think about this in order to do the antiderivative as y to the negative 2 power. So to do the antiderivative, I would add 1, which gives me y to the negative 1, and then divide by that new power. So I get negative 1, y to the negative 1, equals the antiderivative of 1 over x minus 1 would be the natural log of the absolute value of x minus 1. And I'm going to put my plus c to save a spot for that my missing constant. Now I'm going to take a detour, and I'm going to go ahead and find the value of c using the initial value from the instructions. So one thing that I always find easier when I'm actually going to plug in numbers is to rewrite negative exponents as fractions. So I'm going to think about this as negative 1 over y. When I plug in my number, I'm going to have negative 1 over 3 equals the natural log of 2 minus 1. Now 2 minus 1 is just 1, so I don't need the absolute value anymore. The natural log of 1 is 0, so I'm going to have c equals negative 1/3. That's my detour to find my c. I'm going to go ahead and plug my c back in. So my new equation would be negative 1 over y. Remember, I rewrote the negative exponent in the denominator equals the natural log of the absolute value of x minus 1 minus 1/3. Now, in order to get y by itself, I'm going to do two things. I'm going to multiply by y on both sides, and I'm going to divide by the natural log. So when I multiply by y, I get negative 1, because the y's cancel, equals the natural log of the absolute value of x minus 1 minus 1/3 times y. And now to get y alone, I'm going to divide. So y equals negative 1 over the natural log of the absolute value of x minus 1 minus 1/3. And that would be my answer. Okay, let's take a look at the next question. So this is again a very typical AP free response question with a slightly different take on differential equations and how these ideas are connected. So this was from the 2017 AP test. It was question number 4. And it says, at time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius at time 0, and the internal temperature of the potato is greater than 27 degrees Celsius for all times. So it never gets colder than 27. The internal temperature of the potato at time t can be modeled by a function h that satisfies this differential equation, where h is measured in degrees Celsius and h of 0 equals 91. So, unlike in the previous problem where they just said, consider the differential equation, they've given you a whole story here, but they've still given you a differential equation, so a derivative, and they've still given you an initial value, h of 0 equals 91. Part A says, write an equation for the line tangent to the graph of h at t equals 0. Use this equation to approximate the internal temperature of the potato at t equals 3. This should remind you a lot of part B in the previous question. There are two parts to this question. Write the equation for the tangent line, and separately, use this equation to approximate the temperature at 3. So that means we're going to do this in 2 steps. Step 1 is to write the equation of the tangent line. Anytime you need to write an equation, you need a point and you need a slope. Now it tells me to write the equation of the tangent line at t equals 0. So 0 will be my input. I'm also given the initial value in the instructions that when 0 is the input, 91 is the output. So that's my point that I'm going to use. To get your slope, you want to show that you understand that the derivative is the slope of a tangent line. So you want to make sure to label and show your work carefully here. And we're going to evaluate this at 0, 91. Now here is one place where some of these problems can get a little tricky. In this problem, h is on the top and t is on the bottom. So h is like having a y and t is like having an x. In this equation, then, it means we need to plug in the y value for the h, which is the 91. So I would have negative 1/4 times 91 minus 27. What that means is that I have negative 1/4 times, and 91 minus 27 would be 64. So I get negative 16 as my slope. Finally, my tangent line would be y minus 91 equals negative 16 times x minus 0. There's the first part of my answer. Now, the second part of my answer is to figure out what the approximated value is when t is 3. So I'm going to take this equation and rearrange it a little bit. Y equals -16. I'm going to change for now I'm going to leave it alone, plus 91. Now I'm going to change this so that I have the correct variables for this problem. In this problem, we're using h's and t's. So I would say h of 3 is -16 times 3 plus 91, because 3 minus 0 is just 3, which means I get -48 plus 91, which means I get 43. So I estimate that 3 minutes later, the temperature of my potato would be 43 degrees Celsius. Now let's see if this makes sense. If you take a potato out of a pot, should it get hotter or colder? We're starting at 91 degrees, and now 3 minutes later, we're at 43. It kind of makes sense to me that we're going to get a lower temperature if it's been a while since we took it out of the pot. Part B says use the second derivative to determine whether your answer in Part A is an underestimate or an overestimate. So it's giving you a hint here about what you're supposed to do, and this is a place where we will review something that we learned earlier this year. The hint it's giving you in the question is use the second derivative to determine whether your answer is an underestimate or an overestimate. If you need to use the second derivative, then the step 1 would be to find the second derivative. So if I want to find the second derivative, I'm going to take the derivative of the equation I already have. Here's one thing I want to remind you of from earlier this year. Remember that h is really like having a y. Anytime we take the derivative of a y, we have a special rule. We need to use something called implicit differentiation. So we said if you take the derivative of y, you have to multiply by dy over dx. If you take the derivative of h, you have to multiply by dh over dt. Here's how I would start. Before I take the derivative, I'm going to take this equation that I already have and I'm going to try to make it a little bit simpler. So rather than having a fraction on the outside of the parentheses, I'm going to go ahead and just distribute it to the parentheses. I'm allowed to do that because there are no powers outside here. If there was like a squared here, I wouldn't be allowed to just distribute. When I distribute, I get -1/4 h plus 27 over 4. Now when I go to take the second derivative, it's a little bit easier because I can see that it's just take the derivative of the first term and then take the derivative of the second term. The derivative of -1/4 h would be -1/4, but here's where implicit differentiation happens. Since h is acting like a y, I need to multiply by dh over dt. The derivative of 27 over 4 would just be 0. It's gone because it's just a number. Finally, in order to get my second derivative, I'm going to replace the dh over dt in this equation with what I already know. And what I already know is that dh over dt is this. So I'm going to replace this with -1/4 parentheses h minus 27. Now I could simplify this. I could say, okay, -1/4 times -1/4 would be 1 over 16 times h minus 27. It looks a little bit neater that way. That's the way you usually see it written in the answer keys for the AP test. And that would be my second derivative. Now, that's kind of part 1. Use the second derivative. And on the AP test, you will get partial credit for finding the second derivative correctly, even if you didn't remember how to use it to find the under and overestimate, whether it's an under or overestimate. But here's what we need to know. We can use the second derivative to determine if our tangent line is an under or an overestimate because the second derivative tells me about concavity. If the graph is concave up, then all of the tangent lines will be below the curve. And if the graph is concave down, then all of the tangent lines will be above the curve. So if the graph is concave up, I'm going to have an underestimate, and if the graph is concave down, I'm going to have an overestimate. Here's how I figure this out. It says in the original instructions that the value of h is always bigger than 27. If I plug in a number that is always bigger than 27, then this answer is always a positive number. So this is greater than 0 for all h bigger than 27. Since this is positive, I'm going to have a graph that's concave up, like a cup. So all of my estimates will be underestimates. Here's where I write out the second part of my answer. Is it an underestimate or an overestimate? So I would say part A is an underestimate because the second derivative is greater than 0 for all h values that are bigger than 27. Last but not least, part C. So in part C, it says for T is less than 10, an alternate model for the internal temperature. So a new equation that does the same thing. A new model for the same thing, the internal temperature, is the function g, which satisfies this differential equation. So they're giving us a new differential equation. And g of t is measured in degrees Celsius, and g of 0 is 91. So they're giving us a new equation with the same initial value, 0, 91. It says here, find an expression for g of t. Find an expression for g of t means find the original equation. So we need to think, if we've got the derivative and we want the original equation, we're going to need to use separation of variables. So that's part 1. Part 2 is, based on this new equation, what is the temperature at t equals 3? So that's part 2. After I have this equation, can you find the temperature now? Let's start with part 1. Can you find the original equation? Because we can't do part 2 without it. So I'm going to take my differential equation, dg over dt equals negative g minus 27 to the 2/3. Again, we have two variables, g and t, so we need to get them separated. So I'm going to have 1 over g minus 27 to the 2/3 power times dg equals, now there's a little invisible -1 here. It's not just a negative, it's a -1. So I'm going to keep that on this side and have a dt here. Step number 2 is going to be to integrate. And I think it's easier to integrate if I envision that this is g minus 27 to the -2/3. So what I'm going to do is add 1, which means I get g minus 27 to the positive 1/3, and divide by my new power, which is 3. I'm also going to consider chain rule, but since the derivative of g would just have been 1, I'm not going to worry about that here. Equals -1 becomes -t plus c. Now I'm going to take a detour. I'm going to go find my c. So I'm going to plug in my 91 and my 0. I have 3 times 91 minus 27 to the 1/3 power equals 0 plus c. 91 minus 27 is just 64. So I have 3 times 64 to the 1/3 power equals c. The cube root of 64, because a 1/3 power is really a cube root, would just be 4. And 4 times 3 is 12. So now I know that my c is 12. I'm just going to resubstitute that back into the equation. So I'm going to have 3 parentheses g minus 27 to the 1/3 equals -t plus 12. And now I'm going to get g by itself. So I'm going to divide everything by 3, which means I have g minus 27 to the 1/3 equals -t plus 12 all over 3. And then I'm going to cube everything because the opposite of a 1/3 power is a third power. So I'm going to raise cube both sides, which means I have g of t equals -t plus 12 all over 3, the third power. This, I'm going to put a box around. That's the answer to the first part of the question. Find an expression for g of t. Now, the second part of the question says, what is the temperature at t equals 3? So to figure that out, I would say g of 3 equals, and I would plug the number 3 in. So I'm going to have negative 3 plus 12 all over 3 to the third power, which means g of 3 equals 9 divided by 3, which is 3 cubed, which is 27 degrees Celsius. That's the second part of my answer. Now, here's the part that I think is really cool. In this situation, we can actually use part A to check part B to check part C. We said our tangent line's estimate was 43 degrees. We also said that this was, did I do something wrong here? What did I do wrong? 64, 12. Oh my gosh, you guys, I'm so sorry. This should be, instead of g of t, this would be g minus 27. And then I would need to add the 27, geez Louise, to the other side. So this should be g of t equals this whole thing plus 27. I am so sorry. I'm not going to remake this whole video to show you that I added the 27. I am so sorry. See this minus 27 here? I cubed it and I got so excited that I forgot about the minus 27. Bah! But let me tell you how I knew I made a mistake. If I add the 27 here, it changes this answer to a 54. And here's why I knew I made a mistake, which is what I was wanting to teach you anyway. This said the answer should be 43, and this said that should be an underestimate. If this is an underestimate, this answer should be bigger than that number. So if I got 27, I knew I made a mistake. That was kind of my clue. I had to go back and look to figure that out. That was a happy mistake because I could really show you how that works. This should actually be 54, which makes sense. If the estimate was 43 and that was too small, this number should be bigger. Oh, what a happy accident. I mean, an accident, but a happy accident. So again, I cubed it and I forgot about the minus 27. I needed to add that to the other side. And I figured out that I made a mistake because when I went and I substituted and I got my estimate, then I realized that it had needed to be bigger than 43 and it wasn't. Anyway, thank you guys so much for watching. I know this is a longer video, but I do appreciate it. This is really going to help us get ready for the AP test. I'm trying to show you how to kind of break down these questions into their parts and how to then attack the questions using what we know. So I look forward to seeing you in class, and we will practice this a lot. See you soon.